Our next problem is called implement a trie or a prefix tree. Basically, a trie, pronounced as trie, or a prefix tree is a tree data structure used to efficiently store and retrieve keys in a data set of strings. It is being used for things like autocomplete or spell checker most commonly. We have to implement a trie class, basically containing a constructor, and then we have like three methods. The first method will insert a new word inside the trie, and the search and starts with will basically perform a search on that on inserted words. So in the search, we are searching for the exact word inside the trie, and for the starts with, we are basically doing the prefix part of the prefix tree. So we are checking if there's a word that begins with a certain prefix. If there is, we return true, and if it doesn't, like, we just return false. So here in example, we are basically just constructing first trie, and then we are inserting apple. And when we try to search for apple, we will return true because we are searching for the exact word apple. Now, in the example of searching for app, we will return false because we don't have the exact word app inside the trie. When we do the prefix search for app, basically apples is prefixed by the app, so we return true. Next, when we try first to insert the app inside the trie and then search it, we will get the true because that word exists inside of that trie. Now we'll see what do we have for the constraints for this problem. And the constraints are the following. The word and the prefix that are being used to insert or search inside the trie are from 1, their length is from 1 to 2000. The word and prefix consists of only lowercase English letters. So this is basically when we are dealing with tries, it's the first question that you should ask is like, what does the string contains? Like what does the string consist of, basically? So in this case, it's only lowercase English letters. Now we also have that we will have at most 3 times 10 to the 4 calls in total will be made to insert, search, and start with. When it comes to tries, there are 2 things that we have to define. We have to define the children relation. So how many children a node can have, because basically tries are kind of similar to binary trees, but the only difference is that they can have as many children as we want. So each node can have as many children as we want. So how do we define the children? And then the second, what additional kind of data are we storing for each node? So basically that's the data that we are storing in each node depending on the problem that we have. So in this problem, we have to solve the insert. So how do we insert into a trie? And then we have to basically implement the search and starts with. So prefix and the complete search. For the complete search, basically we have to know that a certain node represents the end letter of a certain word that has been already inserted in a trie. So for each node, we will have the array of children, basically the relation to the children, and we'll also have the indication, a Boolean flag, whether that node is an end letter of any of the words that have been inserted into a trie. That's basically enough to perform the search for the word. For the prefix, basically we don't have to check if the node is marked by that flag. It's just enough to find some sequence of characters that represent the prefix. If you find it inside of the tree, that basically means that there is a word that starts with that prefix. Now we will go through an example of how we insert and how we search inside of the tree. So let's just say we are inserting the word car and the word app and the word apple inside of the tree. So because we have only lowercase English letters, we can define the children relation as for each node as a constant size array of 26 letters, because that's the maximum of children that we can have, because those are all the letters, lowercase letters in the English alphabet. So we'll start with our root, and then while we are inserting, we will be creating a new node if it already doesn't exist. So for example, for the first letter, we will have C, and we will just insert it here. And then we will basically continue, because we don't have an A after C, we will just insert A, and then we will insert R. Now, when it comes to the second word, we will check if we have a. We will again start from the root. I will check if we have a node with value a. We don't, so we create one, and we continue basically to do the same for the rest of the nodes. Now for the apple, we already have a, p, and p. So the only thing that we have to add is the l and the e. And basically this will be the representation of app, but this will be the representation of apple. And also for this node, we will have a special tag isWord, and it will be set to true. The default value will be false. So here we'll have false, here we'll have false, but here, because this is the end of the app, it's a word that has been inserted in the try, then we will also have true here. So then when we start to basically search for a certain word, let's say we are searching for a word car, we'll basically iterate over each letter, and we will move throughout our try. So basically, we are looking first for, we are starting from the root, and we are looking for the letters C, the node that corresponds to the letter C. In this case, that's this node. So we have that node, and we can continue with the iteration. So then we start from that node, and we check if we have A. We have A, and then we have R. So for example, if you try to search for a word, cars, for example, we will come to R, and we will check if we have the node with the letter S, with the value S. In this case, we don't. So basically, the search will just return null, and we will know that there's not an exact word that that corresponds to cars. Basically, it hasn't been inserted into the try. And if you're searching for the exact word, we have to check if this node has the isWord set to true. If it does, then we basically know that the word exists inside of the try. If you only search for the prefix, it's enough basically to get to the end letter. So in example, if you are searching for prefix AP, we'll just go to AP, and we'll basically have A and P. So basically there is a prefix. There are some words, in this case app and apple, that are prefixed by AP. So we'll just return true. But if our prefix is, for example, DE, we'll start from the root, and we'll check for D, but we don't have D. So basically, we'll just return false. Now, when it comes to time and space complexity, basically here we'll have reads and writes. So if we mark them by read and write, and both of these operations will be dominated by the number of nodes that we have inside of the try. So no matter how many times we call it, basically if we mark our number of words that we are inserting into tree by n, let's just say, and the average length of the word will be L. So for us to build the try and insert all the words, we need n times L time complexity. The same goes for the word searches. So if you have n word searches or n prefix searches, and the average length of the word is L, then for each word we'll basically spend L nodes to perform the search. So basically, we can also say that this is the sum of the lengths for each of the words that we have. So basically, that's our time and space complexity, because at the end, the try will contain all of these words that have been inserted to it. So first of all, we have to present our try nodes in some way. So for that, we will define our private class called try node. And for each node, we will basically have to define the number of children. In this case, the constructor will just initialize the number of children to an array of try nodes. So each node can contain 26 children in total, which corresponds to the number of lowercase English letters that we have. Besides that, we also need some additional data, because we will be searching for exact words. We have to mark one of the nodes that's basically represent the end letter of a word that's being inserted in the try. We have to represent it by some flag. And to represent it, we are using isWord, and the default value will be false. Next, we will define our try node root, which will basically be just a starting point for each of the operation that we'll have on the try. In the try, we'll just initialize that root to a node, try node. Next, for the basically for search and start with, they're basically the same, almost the same methods. The only difference is basically that for search, we have to check if the isWord is set to true. So to not repeat our code, we will just define search prefix, and we'll pass the prefix as the argument. So we are just trying to find the prefix, and we will use this method for both the search and starts with method. So we'll start by declaring our iter to be pointing at the same location as the root. So we are starting from the root, and then for each letter in the prefix, we will first get it, and then we will basically check if it's defined. If we have if the current node has the child node that corresponds to that letter. If it doesn't, we will just return null because we don't have that prefix. We don't have the next letter in the prefix. But if it does, then we'll just move to that node, and to move, we can use the children array relation to basically just move to it. Then after we are, if we crossed all of the letters inside the prefix, basically the current node will correspond to the last letter that we have observed, the last letter of the prefix. Next, we insert. We will basically have a similar logic. We will start from the root, and then for each of the letters inside of the word, we will first get it, and then we will check if it's undefined, if it's currently undefined. So if we don't have it inside of the trie, if we don't have it, then we have to create a new node for the new child node for the current node that corresponds to that letter, and then we basically move to that new node, so we can start from the next letter of the word. Finally, we'll just put the last node will be pointing to the we'll have the value of the last letter inside of the word, so we just put the flag is word to true. Now for the search, we'll just use the search prefix. We will pass the word that is given to us by the first parameter to this search function, and the search prefix will return the node that corresponds to the last letter inside of the word, if such exists. If it doesn't exist, then we'll just return null. So first of all, to be sure that the node is not null and that we have that certain prefix, we'll check if the node is not null. And then, because we have to have an exact word, we'll check if the node has the flag is word set to true. If it is, then basically that means that the word has been inserted inside the trie. Next, we'll start with, basically we have the same thing as for the word, but in this case we just use the search prefix method, and we just pass the prefix that's given to us by the input parameter, and we just check if the return value of that search prefix is not equal to null. Basically that means that we get the last node that represents the last letter of the prefix, so we can be sure that there are some words, multiple words, or only one that starts with this certain prefix. And that's basically all of the operation that we have to implement.